Welcome to this mini class in which we're going to cover what is pump head. And I'm pretty sure that you have heard this concept in your fluid mechanics lectures, or maybe in some classes regarding pumps, or maybe even when you try to purchase your pump for your domestic use. Now, we're going to try to make this clear mathematically, but also trying to make sense on what's happening in the fluid mechanics level, but more importantly, having a grasp or general understanding on what is indeed pump head. And the very first thing that comes up to mind is, this little face right here. So here is the head. And no, I'm not joking, guys. Actually, whenever I ask what is the pump head, there's a lot of students that try to figure out exactly which part of the equipment or which part of the pump we are talking about. And actually, pump head is not a physical concept that is present in the equipment of the pump. So in this specific case, we have a suction line right here and a discharge line. We got this centrifugal pump. The impeller is inside. We got a shaft right here. Then we got the connection between the driver and the shaft and the motor. So generally speaking, let's continue. A head is nothing more, something that is used to refer to the total height that, theoretically speaking, a pump could rise. Now, this is very helpful because if you're working with domestic use of the pump, you want to know if the given pump is going to be able to get the desired gallons per minute, let it be flow rate, all the way to maybe the second floor. That will be something around 6 meters maybe, or something around 18 feet. So in this specific case, maybe you're looking for a 5 to 10 gallons per minute, a pump that is able to get to this head. And actually, this is the main idea, to be able to compare different pumps and different systems directly to the total height that theoretically or hypothetically could be rising the pump. Now, why do I say theoretically or hypothetically? Is because in real life we do not operate pumps at the top level. So meaning that we want to deliver exactly in that point the total flow rate. No. In reality, we're going to have a continuous flow. So, well, this is just to have a general understanding, but don't think that we actually design pumps for this specific requirement on height. Okay, so that's the general idea. Also, you could see this more on the theoretical energy level. Let it be, it's the essential energy per unit weight that the pump imparts to the fluid. So now we're getting, let it be energy, will be joules, maybe joules per second. Per unit weight, let it be kilograms. So now it is getting to get a little bit more sense, but at the same time is getting way on the other side because we were talking about height. Now we're talking about joules per second per kilogram. So you can see why there's a lot of confusion in the term of pump head. Now, the important part right here is to understand that the energy will allow the fluid to overcome the resistance and reach its destination. Now, the idea of the vertical pump is to ensure that there's only one resistance, which is going to be the potential energy, or the delta Z, which is, I don't know, let it be CA all the way to CB. And of course, we're ignoring changes in pressure. Let it be atmospheric pressure is going to be here and here. Let it be the same suction pipelines or tanks, so the velocities are the same. And friction, we're ignoring friction for now, or at least assuming the friction comes in a very small amount. So what we're talking about is the real resistance is that of the height. It's typically measured in units of length, such as feet or meters. So that's also very confusing for a lot of students. Why are we measuring power or capacity of a pump that delivers meter or feet? Is it horizontal ones or vertical ones? Yeah, that may not be quite the best option. I also like to call this the total work per unit mass divided by gravity and density of the fluid, let it be the specific weight. So yeah, specific weight can be related. Actually, I always say that head doesn't make that much of a sense if you don't know which type of fluid you're working with. So whenever you see head of a pump or commercial pump, this is typically based on water. So ensure that you are working with the fluid that you need to work on. So for instance, if you're working with certain type of gasoline or fuel oil, or maybe an alcohol, organic materials, ensure that the density or specific weight is similar, or you need to fix compared to that of water. And more importantly, guys, when we're talking about pumps, we talk about head, and we can have a head loss due to friction, we can have a head removal due to turbines, we can have a head gain due to a pump. So whenever we talk about this capacity or the pump head, we can say that this is the total dynamic head. And we're going to see some diagrams explaining what are the different type of heads and why this one is the most convenient one for us. So as stated, guys, we will never operate this way. Another way to approach the understanding of pump head will be the simple answer to the question, what is the question? So if pump head is the solution, what is the question? Well, pump head represents the total work done per unit fluid by the pump. So we're talking about pump, we're talking about a fluid, and we're talking about work going into the fluid. So this may be kind of confusing because then we're talking about the work into the pump or the work into the fluid. Okay, and well, once again, we have our pump right here. We have vertical operation. There will be no flow rate. And remember that if there is no flow rate, there is no friction because there is no flowing through the tube. And then we got our mechanical energy equation, removing the pressure. There's no difference in pressure. Velocities, assuming that these are stagnant, well, this will be 0. And for now, we are going to ignore the friction right here. And there are clearly not turbines or any kind of equipment that is removing energy. So we have a summarized version of the pump head. Once again, the difference in height. So why is it expressed in units of length, meter or feet? Could also be other unit, but these are the typical ones, SI units and English or imperial unit. This practice comes from both the mechanical energy equation. We want to force this part right here. We saw that in the unique case in which we operate the pump vertically, which of course is not most of the cases, but definitely there are at least 80-90% of the cases that we could theoretically say that we are operating near this case. So it makes a lot of sense to work with height. Just assume pump power to height. It makes a lot of sense. And also in the practical engineering sense, that it's always way easier to know that pump has the capacity of X flow rate, go to the second floor or the second. So yeah, that's the way in which you could be playing as an engineer. Or maybe we have the same fixed amount of height, let it be 10 meters, but this pump has a lower flow rate capacity than the other pump. So you can compare pumps very easily. Actually, I love this because once you're looking for pumps, the only thing that you're looking for is a relationship between head, flow rate, efficiency, cost, and power. Essentially, technically speaking. Of course, there's a lot of pump performances indicators that we're going to see later on, but for now, those are the main issues that you want to compare. Okay, hey there. I hope that you're enjoying so far the course because this is just a preview that I uploaded to YouTube. So if you want to check out the full content of this course, maybe you're looking for a specific problem or a specific solved exercise, or just to know all the theory and structure, ensure to check out this link right here. Now, of course, you will get access to all the full dynamic video lectures. I've also added some text and summaries in each specific lecture. We have a lot of solved exercises, all explained step by step. A lot of downloadable material, for instance, the equation booklet, the spreadsheet that are modeling certain type of systems or so, PDF sheet, and industry vocabulary. Not only that, in order to evaluate yourself, we have prepared some quizzes so you ensure that you are learning all way long. And finally, guys, the top question and answer for job interview. If you are going to take this to the next level, you're looking for a job, and you know that you require this knowledge, you are going to get some very useful questions. I hope that you enroll in the course, and I'll see you in class. And now, guys, let's get technical because I told you that we have the so-called total dynamic head, because the total head of the pump will depend a lot on the case that we are analyzing. So we got case number 1, case number 2, and case number 3. Okay, but definitely, as you can see, there are 3 main cases. The first one has a very small amount of fluid. So let's say that we have the same pressure in the 3 tanks. So pressure is definitely not something that we can consider. But what we are definitely considering is the height of the fluid. So we know that we are kind of cheating if we have a higher level. For instance, H3. This will have a delta C, which is going to be pushing and hence will be increasing the height of this pipeline. So try to imagine that you are a pump manufacturer and you don't know how the client is going to be adjusting their levels in this specific case, because then we have a lot of cases. We have tanks, we can have pressurized tanks, we can have fittings, valves, we can have very long tubing systems. So it will be always hard for us to know the system that our client will be working. So the only thing that we can actually manage is try to ignore this part right here and actually account for this part right here, which is called the total head. So let me remove all this part right here. And as you can see, the total head is always the same. If we were to measure this numerically, this will be 10, this will be 10, and this will be 10. And actually is the only thing that is fixed, because H1 could be 2, H2 could be 4, H3 could be 6, and hence, if this is always fixed, 10, 10, and 10, then the total height will be not always the same. Actually, this will be 12, this will be 14, and this will be 16. So the only thing apparently that seems to be remaining the same, that is the total head. Okay, so the suction head is something that it is not quite reliable, and the discharge head is not quite reliable. So the pump manufacturer went to tell you how much head their pump will produce. So that's the main objective. They want to tell you a concise value. But unfortunately, they don't know what type of water supply will be available, if you're going to be using water. So they cannot do the correct calculations. But fortunately, there's a very ingenious and simple approach. And what they are going to be doing is they will be subtracting the head available at the suction, which is this one right here, the so-called HD1, and the head produced at the discharge. So essentially, we will have it right here. So the total dynamic head, which can be also HA in our variables or our equations, will be the discharge head minus the suction head. Then, thankfully, it doesn't matter what the suction tank level is. They are telling you only what the pump can do, regardless of the water supply pressure. So yeah, here we have a low pressure on the suction line, we have a normal pressure in the suction line, and we have a very high pressure in the suction line. Hence, we're going to have different values. And as stated before, the only point that remains is total head. So thankfully, we have a turnaround when we're talking about what is the total head of the line. Now I'm going to go reverse. What will happen in this specific case? All were levels above the suction line, but what will happen if we have a level below the line? So this is not great news. The pump will still produce the same total head. That's the great point. So the total head, if this is the same scenario, this will be 10. But the discharge head will be lower, and makes a lot of sense. Let it be, this is -4. So then this must be 6. And actually, if you were to add this 4 plus 6, this will be equal to the 10th value right here. This means you may not have enough pressure to run your devices. And this is something that we are going to cover later on in cavitation. So whenever you have a very high length between your suction line and the bottom, it may cause a lot of problems, okay? You may need to consider getting a pump with a higher total head or a better specification, or simply adjust the level of the pump. But still, the main idea remains, guys. Total head here is the same as total head here and here. So it's essentially what's the input of the pump. I remember that we started this lecture stating that there was no flow rate, and as you can see here, yes, actually we have a fixed level, there is no flow rate, but in real life, guys, we know that there is actually flow rate. So let's see how to account for the flow. And now I want to present you the case in which we have flow rate, and then compare it with the previous one in which we didn't have flow rate. And I know that I started with the theoretical idea or hypothetical that there is no flow rate, but in real life, we always have flow rate. When we have flow rate, we have something called friction head, because there's friction due to flow rate, okay? So assume we have a system such as the left with no flow rate, where the discharge pipe is high enough that we have counted the balance between the pressure required to go upwards is the same as the pump. Okay, so there's no flow rate. But now, suppose that we have that exact pipe right here, and then we cut it down. Of course, we're going to expect spilling of the pump or flow rate because we have less height. So now let me explain you all the interesting concepts that we need to analyze. So first thing first, we got the so-called suction head. This is fixed. This depends on the tank and will typically be fixed due to level control. Okay, so this is fixed. Then we have the discharge static head, which is this one right here. Discharge static head, which is this one right here. In this specific case, it will be greater than the one that is flowing. Why? Because friction head is going to making smaller the discharge static head. So yeah, this one right here is exactly as this one right here. And the most important part right here, guys, and the one that I want to focus is how do we measure the total static head, the total head with flow, and the total head without flow right here. So these are the three main concepts I want to show you. This one is a theoretical one. This is not going to happen because we don't have a system in which there will be stagnant flow rate. Then we have this one right here, the total head with flow. This is the one that is going to be reported with the friction and the total static head. And then we have this value right here, the total head with flow. Now, what's the only difference between this part right here and this part right here? Well, there will be a decrease because there's flow rate. But not only that, guys, if you want to calculate the total static head and the friction head, that will be exactly what we're looking, the total head with. So that will be the general idea I want to present you in this specific slide, guys. I know that this may be a little bit confusing, but once that you get started with calculations and get started with selection of pumps, this is going to be piece of cake. Now, let's make some remarks on the things that we just studied. So first thing first, this lowers the overall total head, so overall total head, and flow starts to come out of the pipe. Okay, so now that we know what is pump head, how to calculate it, the importance on the suction line, discharge lines, and if there's flow rate or if this is static, we already know all that, right? But why do we need pump head? Yeah, maybe to select between pumps, but in reality, this is by far one of the best criteria to select pumps. So if you understand pump head and volumetric flow rate, you're almost set up for pump selection. Now, choosing a pump with the inadequate, or let it be a lower head than required, is going to cause you a lot of pain because you're not going to be able to sustain operation. You're going to have a lot of friction losses, you're going to be operating most likely in the lowest efficiency point, and you will not deliver the required flow rate. On the other hand, if you choose a pump with a lot of excess head, you're going to have excess, as the name implies. But this will result in unnecessary energy consumption. You're going to have higher costs. You will need to increase the friction of your system in order to account for the given flow rate and pump power. And last but not least, guys, why do we prefer to state pump head rather than pump pressure? And this is a very common question that I get a lot. Why aren't we focused in power or pressure? So typically you're interested on what is the maximum pressure of a pump. Yes and no. So the term head is preferred over pressure in pump evaluation applications. As stated before, it's way easier to compare between pumps and systems rather than to compare the discharge pressure of several pumps. Head provides a very practical measure of a pump's capacity. So this is very important, capacity, to perform tasks such as lifting fluids to a higher level. In this specific case, that we want to do so. Now, pressure does not account directly for friction losses or changes in velocity or height. It is only a parameter, remember. But head does account for all those parameters. We account for friction loss, elevation change, pressure changes, velocity changes, and so on. Head remains consistent regardless of the type of liquid being pumped. As long as viscosity is low and similar to water, you can compare several pumps, verify whether or not they are going to perform the required. And finally, guys, pressure at the discharge point may vary between different liquids. This is the most important part. Depending on the density, viscosity, of the fluid, you're going to have several pressure differences. And this is the main issue. You are not going to be able to change the fluid or compare different fluids between the pump capacities, which is in many cases very important because you have a fixed pump and you're just asking yourself, maybe you're working with a sludge that varies its density or viscosity. It is way straightforward to simply adjust the specific gravity rather than to recalculate everything in order to get the calculations for the second properties. And hopefully it is clear by now, guys. I know that this was a very theoretical lecture, and yes, this is the main intent. We need to work with our analytical thinking, but also we're going to be working with a lot of problems, and hopefully if you're of those type of students that prefer to do some numbers, understand graphs, and make some calculations, we're going to continue with that, and the explanation is going to get way easier and clearer. Make no worries, guys, we are not done with pump head. We're going to be making more exercise. But hopefully by now you understand that pump head is one of the most relevant pump performance indicators, and more importantly, one of the top criteria for pump selection. I really hope that you enjoyed this mini lecture, guys, and if you want to learn more about pumps, how to design them, how to select them, and how to optimize them, ensure to check out this course because that's exactly what we're going to be doing. On my behalf, guys, that will be it. I'll see you in the next video.